In this video, I'm going to talk about random variable. Let me ask you, what is the difference between random variable and variable? You can pause the video and think about it for a while. Suppose we have a quadratic equation, ax squared plus bx plus c equals to 0. And suppose the solutions are 1, 2. Similarly, we have a cubic equation, ax cubed plus bx squared plus cx plus d equals to 0. And suppose the solutions are 1, 2, and 3. Now my question is, are these random variables? The answer is no. These are just the variables. These are not random variables. Random variables have probability attached. For example, you roll a dice. The sample space would be 1, 2, 3, 4, 5, and 6. So each of these outcomes has probability attached. Like if you want to get 1 on the dice, the probability is 1 over 6, right? So there is a probability attached. Also, random variables are alternate representation of events through numbers. So alternate representation of events through numbers. So for example, you toss a coin twice, the sample space would be HH, TT, HT, and TH, right? Now let's define an event of getting heads. So you can use different capital letters to denote the number of heads. Like when there is 2 head, you can use A. When there is 1 head, you can use B, and you can use different capital letters. But there is a limitation on the capital letters. We do not have infinite number of capital letters available, but we do have infinitely many numbers which we can use to denote the event. So for example, in this case, we can use 0 to represent no heads, 1 for 1 head, and 2 for 2 heads. Okay, so this is how random variable is used to represent events through numbers. Now there are 2 types of random variables. Actually there are 3 types, but we are only going to discuss 2 types. So first type is discrete random variable, and the second type is continuous random variable. In a discrete random variable, points are known. Points are known. For example, temperature of air conditioner varies in a discrete manner. So temperature of AC varies in a discrete manner. For example, it can be 16 degrees Celsius, 17, 18, so on, right? So it varies in a discrete manner. In continuous random variable, interval is known. Interval is known, or range is known. We know the range, but we do not know the points. Okay. For example, temperature of any place. Temperature of, suppose, Delhi. So we can quote the range, for example, um, from 15 degrees Celsius to 30 degrees Celsius. So this is the range of temperature in Delhi. Okay. I mean, you can also quote the point, uh, but it can vary in decimals as well. Like the temperature of a place could be 15.56, 15.57, and it can vary in decimals as well. So you cannot exactly quote the temperature, right? I mean, you can say that at this moment the temperature is this, but in the next moment the temperature will be different. Therefore, for simplicity, we use range. We treat it as a continuous random variable. We do not say this is discrete. Okay, so this is for simplicity. Another example could be the share market, share price. Although share price varies in a discrete manner, but we treat it as a continuous random variable. All right. And to calculate the total probability in discrete random variable, we use summation. So total probability, we use summation. Okay. And in continuous random variable, we use integration. Okay. Now let's look at the probability distribution function, PDF, of discrete random variable. Discrete random variable. Let's look at PDF. Here PDF stands for probability distribution function. Probability distribution function. Or we can say probability mass function. Mass function. We can use BMF. All right. Notation for PDF, we can use fx. We can write like this as well, or we can use p capital X. This is random variable and this is the point. All right. So in discrete, PDF is basically the probability. This notation actually tells us the probability. Okay. So PDF in discrete tells us how the total probability is distributed among events or random variables. All right. Let's take the previous example. Tossing a coin twice. So the sample space is HH, TT, HT, and TH, right? So we can write in the form of random variables 0, 1, 2 of getting heads. So what is the PDF? So we write the PDF in this way, P capital X X. So what are the points? 0, 1, 2. So what is the probability of getting 0 heads? This is 1/4, right? Because there is one outcome which has no heads, right? When you get tails in both tosses. Okay. So this is 1/4. What is the probability of getting one head? Probability of getting one head is 2/4, right? There are two outcomes. What is the probability of getting two heads? This is again 1/4. Now, the sum of the probabilities or the sum of the PDFs should be equal to 1. If it is not equal to 1, then you must have made some mistake. All right. So you can add this. This is 1. We can write this as px equals to 0 is 1 over 4. All right, because this is the probability. So in discrete, PDF is the probability. PDF stands for probability distribution function. In continuous, PDF stands for probability density function, and that is not the probability. All right, in continuous, we use CDF, cumulative distribution function, to calculate the probability. All right, but we'll discuss the continuous random variable in the next video. In this video, our focus is only on the discrete random variable. Now let's formally define the PDF. So the definition of function fx is said to be PDF if and only if first condition, fx should be greater than or equal to 0, should be positive for all values of x, because here PDF is the probability and probability cannot be negative. All right, second condition is sum of PDF should be equal to 1. Again, this is the probability, so the sum of the probabilities should be equal to 1. If it is not equal to 1, then that function is not a valid PDF. That is a function, but that is not a PDF. Okay, now let's look at the graph of PDF. So graph of PDF, we take the previous example. So 0, 1 and 2, probability is 1 over 4, 2 over 4 and 1 over 4. This is equal to 1, right? So let's plot this in the graph. So on the x-axis, we have the random variable x, and on the y-axis, we have the PDF, or the probability. So when it is 0, the probability is 1 over 4. When it is 1, the probability is 2 over 4. And when it is 2, the probability is again 1 over 4. Now we can simply connect these points to the point on the x-axis, connect these probabilities to the point on the x-axis. So this is how we can connect. You can also draw the bar. So you can draw like this. Okay, or you can simply drop a vertical line on the x-axis. But you should not join these points. These are discrete. Okay, this is not continuous, so please keep this in mind. You should not join these points. Okay, so the graph in discrete is simply line or bar graph. So this is line or bar graph. All right, now let's do a few problems so that our concept can be, we get the clear understanding of PDF. So let's do a few problems. Suppose we are given a function fx equals to x minus 2, 5 divided by 5, for x equals to 1, 2, 3, 4 and 5. Now we need to check whether this function is a valid PDF. So we can put the values. F1 equals to 1 minus 2 divided by 5, which is minus 1 over 5. Now you can see that the first condition of PDF is not valid here. This is negative, right? But the PDF should be positive in all cases. So this is not a valid PDF. due to the first condition. Now let's look at another function. Suppose fx equals to x squared divided by 30 for x equals to 1, 2, 3, 4. So now let's check this. You can see that when you put these values 1, 2, 3, 4 in this function, you'll always get the positive values, right? So the first condition is valid. Now we need to check the second condition, whether the sum is equal to 1. So sum x equals to 1 to 4 x squared divided by 30, this should be equal to 1. So 1 over 30 plus 4 over 30 plus 9 over 30 plus 16 over 30, and this is 30 over 30, and this is 1. So this is our valid PDF. All right, let's do one more question. Suppose the function is 1 over 4, let's say 1 over 4 for x equals to 1, 2, 3, 4. Now for these values of x, the fx will be the same, right? This is a constant function. So the first condition is valid, it is positive. Now what is the sum? So x goes from 1 to 4 and fx is 1 over 4. So this is again 1, right? Because you are going to add it 4 times. So this is 1. All right. So this is a valid PDF. Now let's move on to CDF. CDF. We are talking about the discrete random variables, so please keep this in mind. First we covered PDF of discrete. Now we are talking about the CDF of discrete. So CDF stands for cumulative distribution function. Cumulative distribution function. In discrete, in this CDF, we do not use very often. In continuous case, the CDF makes much more sense, because in that case, the CDF gives probability. But in discrete, PDF makes more sense, because PDF is the probability in discrete case. Okay, but we are going to look at this CDF as well. So the notation for CDF, we use the capital F, or we can write like this, or we have a different notation, up to x. So CDF is basically, we are going to add the probability up to point x. Okay, up to this point, we are going to add the probabilities. Cumulative, right? So let's look at the formal definition of CDF. A function fx is said to be CDF if and only if, you can write double F, if and only if, first condition, it should be positive for all values of x. Again, this is the PDF is the probability, right? And we are going to add these probabilities, so this should be positive. Second condition is, it should be a non-decreasing function of x. A non-decreasing function of x. Non-decreasing doesn't mean increasing. Non-decreasing means either it can be constant or it can increase. Okay, now since these probabilities are positive, and when you add the positive numbers, you'll get the positive, right? It will increase, or it can remain constant if you add 0. Okay, and for example, let's take the previous example. So x equals to 0, 1, 2. Probabilities were 1 over 4, 2 over 4, and 1 over 4, right? Now, even if you increase the values in x, if you increase the values in x, it should be equal to 1, right? So for other values of x, the probability should be 0. Otherwise, it will exceed 1. Okay, so in that case, it will remain constant. All right, so cumulative distribution function should be a non-decreasing function of x. Now, third condition is function of infinity should be equal to 1. It means if you add all the probabilities, it should be equal to 1. All right. Now let's look at the proper representation of CDF. We do not write CDF in the form of boxes, right? Like we did in the PDF. We have a standard representation of CDF. So we're going to write the CDF for the previous example, x equals to 0, 1, 2, and the probabilities. So we are going to write the CDF for that example. Fx, we can also use the another notation, p x is less than or equal to x. So we are going to add the probabilities up to point x. So the representation is when x is less than 0, the CDF is 0, because you can see when x is 0, we have the probability 1 over 4. When x is 1, we have the probability 2 over 4. And when x is 2, we have the probability 1 over 4. So when x is less than 0, there is nothing, right? So CDF is simply 0. And when it touches 0 but less than 1, the CDF becomes 1 over 4. Okay. And when x touches 1 but less than 2, this becomes 3 over 4, because you need to add these two terms, right? We are calculating up to point x, that is CDF. And when x is greater than or equal to 2, this should be equal to 1. This cannot exceed 1. All right. So this is the proper representation of CDF. This is how we should write CDF. Now let's look at the graph of CDF. Graph of CDF. On the x-axis, we have random variable x, and on the y-axis, we have the CDF. You can use the different notation. We are going to use this notation very frequently in the continuous case. All right. So when it is 0, this is simply less than 0, right? When x is less than 0, it's 0. But when it touches 0, this becomes 1 over 4. So at 0, this should be 1 over 4. All right. Now, until it touches 1, the CDF remains 1 over 4. So suppose this is 1. So until it touches 1, CDF remains 1 over 4. So from this point to this point, this is 1 over 4. And when it reaches 1, it jumps to 3 over 4. So suppose this is 3 over 4. So there is a jump to 3 over 4. And again, it remains 3 over 4 until it touches 2. So suppose this is 2. This will remain 3 over 4. And then when it touches 2, it will again jump to 1. And after that, it will remain 1 for forever. So we can see this is a step function. This is a step function. So the graph of the CDF is a step function. All right. Now let's do few examples. Suppose you are given f1 equals to 0.3, f2 equals to 0.5, and f3 equals to 0.8, f4 equals to 1.2, for x equals to 1, 2, 3, 4. You do not know the function, but you are given the values of this function. When you put the values 1, 2, 3, 4. Okay. Now you are asked to show that whether these CDF, so whether these functions are the valid CDF. So you can check three conditions of CDF. So the first condition is it should be positive. You can see all values are positive, so this is okay. Now the second condition is it should be non-decreasing. And you can see when x equals to 1, this is 0.3, and when x equals to 2, this is 0.5. So this is increasing, right? When x equals to 3, this is 0.8, again increasing. But when x equals to 4, this drops, again, this is increasing. When x equals to 4, this is again increasing, right? So the second condition is also valid. Now let's move on to the third condition, which is the sum should be 1, right? That is f infinity should be 1. So at x equals to 4, this should be 1, but this is exceeding 1, right? Probabilities should not exceed 1. The sum of the probabilities should not exceed 1, but it is exceeding 1, so this is not a valid CDF. Let's look at the second example. Suppose f1 equals to 0.5, f2 equals to 0.4, f3 equals to 0.7, and f4 equals to 1. Now you can clearly see that in this example, the second condition is not valid because the value of the function has decreased from 0.5 to 0.4. So this is not a valid CDF. All right. Let's look at one more example. Suppose f1 equals to 0.25, f2 equals to 0.61, f3 equals to 0.83, and f4 equals to 1. Now all the values of the function is positive. It is an increasing function, and the sum is 1 at x equals to 4. So this is a valid CDF. All right. So this is how you can check the CDF. Now let's do one more problem. Suppose you are given a CDF when x is less than 1, the value is 0. When x is greater than or equal to 1 but less than 4, the value is 1 over 3. When x is greater than or equal to 4 and less than 6, this is 1 over 2. When x is greater than 6 but less than 10, this is 5 over 6. And when x is greater than 10 or equal to 10, this is 1. So you are given a CDF and you are asked to calculate PDF and also find the values of the following sub questions like P probabilities, values of these probabilities. So when x is greater than 2 but less than or equal to 6, px is equals to 4, and px is greater than or equal to 10. So we are asked to calculate these probabilities as well as the PDF. So let's do this. So how do we calculate the PDF? So CDF is basically the sum of the probabilities, right? So we need to subtract those probabilities in order to get the PDF. So what are the points? When it touches 1, the probability becomes 1 over 3, right? So the point is 1, 4, and 6, as well as 10. So the probability at x equals to 1 is 1 over 3. When x is less than 1, CDF is 0. So this is simply 1 over 3 minus 0, right? And when it touches 4, the CDF becomes half, which means there must be something added that which is why the CDF becomes half, right? So we need to subtract this. So this is 1 over 2 minus 1 over 3, and this is 1 over 6. Similarly, when x equals to 6, this is 5 over 6 minus 1 over 2. So this is 1 over 3. And when x equals to 10, this is 1 minus 5 over 6. This is 1 over 6. Now, whether these PDFs are correct, you can check this by adding the probabilities, by adding the PDFs. This should be equal to 1. All right. So 1 by 3 plus 1 by 6 plus 1 by 3 plus 1 by 6 should be equal to 1. All right. Let's do one more problem. Okay, wait. We need to calculate these probabilities as well. So let's do this. So when x is greater than 2 and less than or equal to 6, so you can look at the table. When x is greater than 2 and less than 6, so greater than 2 means we should include 4, right, as well as 6, because it says less than or equal to 6. So this is simply 1 over 6 plus 1 over 3, these two values, right? Now B, what is the probability at x equals to 4? So this is simply 1 over 6. C, what is the probability when x is greater than or equal to 10? This is 1 over 6, right? You can see here 1 over 6. So this is how you can solve the CDF problem. Let's do one more question. If fx equals to x over 15 for x equals to 1, 2, 3, 4, and 5, and 0 otherwise. Now you are asked to calculate the probability when x is greater than half but less than 5 over 2, given that x is greater than 1. So this is the conditional probability. So let's first draw the table, because it is always easier to look at the values from the table. So when x is equals to when x is equals to 1, this is 1 over 15, 2 over 15, 3 over 15, 4 over 15, and 5 over 15. Now the conditional probability, we know the formula that P when x is greater than half, less than 5/2, and you know that you can treat this as A and this as B. So the formula is probability of A given B is equals to probability of A intersection B divided by probability of B, right? So this is and x is greater than 1 divided by probability of x is greater than 1. So you can see that this is 0.5, right? This is 0.5, this is 2.5, and this is 1. So this is nothing but this is probability x equals to 2, right? Because x is greater than 0.5, less than 2.5, and x is also greater than 1. So it should be somewhere in between 1 and 2.5. So what is the discrete number between 1 and 2.5? That is 2, right? So this is probability at x equals to 2. Now what is at the numerator? At numerator, you can add all the probabilities greater than 1, or you can subtract the probabilities probability at x equals to 1, right? So you can do it either way. You can add all the probabilities at x greater than 1, or you can subtract the probability at x equals to 1 from 1. Okay, so I think this is simple to subtract. So in the numerator, this is simply 2/15, as you can see, 2/15, and in the denominator, this is 1 minus 1/15. So this comes out to be 2/14. If we reduce this, then this is 1/7. All right. So this is how we can solve these CDF problems. So now let's stop here. We'll do some more problems in the next video, and then we'll discuss the continuous random variable. So thank you so much for watching this video.